Okay, so we're on air. So in this unit, we learn about real numbers and the operations that we do with real numbers, most of which you've already done, and so some of it would be review. But the purpose of that is that we need to understand how we do operations with real numbers, so then we can do them with these mathematical symbols that make up algebra, right? And it works the same. So these are the sets of real numbers. You know, I know you've done some of this stuff before. What is a natural number? Go ahead. Counting numbers, right? Counting numbers are the natural numbers. So they start with 1, 2, 3, and then dot, dot, dot. And what do the dot, dot, dot means? It goes on forever, right? It goes on forever. Okay, what are the whole numbers? Adam? So the whole numbers are the natural numbers plus 0, right?
The whole numbers are like just the positive numbers.
Yeah, just like we're showing. It starts at 0 and it goes positive. What do you call it? What do you call it when it also goes in the opposite direction? -1, -2. That's what integers are, right? So integers go on forever to the left. Yes. Yes. There is no last number. That's what the concept of infinity is. Okay, quiet please. So the integers are plus and minus whole numbers. Okay. What are rational numbers? Somebody else. Sid. So like what? Not a great answer, Katie. Fractions, right? Basically, any number that can be written as a fraction is a rational number. So I'm just going to say fractions. We're going to say more about that in a bit. Okay? Yeah, so the irrational means not rational. That's the IR is like a not prefix. And then if you put together all of the real number, the rational plus the irrational, you get what's called the real numbers. Oh, yes, there are. You don't do them in this class, but what do you call numbers that are not real?
Not real numbers.
Imaginary. Imaginary numbers.
Imaginary. Like 43 trillion.
Okay. So here we go. I'm going to draw this like this, right? This whole big block, that's going to be the real numbers. So I'm going to put irrational over here. And then rational goes over here. Oops. Okay. Now, as we said, the integers are all inside of rational. And the wholes are inside of those. And then finally inside of that is natural. So a natural number, for example, is a whole number, is an integer, is a rational number, is a real number. Take for example if I have the natural number 2. Okay, 2 is definitely a natural number, and we know that the wholes are the naturals plus 0, so it's in that set too. how is it that and then integer, because it's plus or minus the wholes, how is it that 2 is a rational number? It doesn't look like a fraction. Adam?
Virtually every number is a fraction because you can put a 1 on it.
Yeah, if you look at it like that, then it is a fraction. So rational numbers include numbers that don't look like fractions but could be put in the form of a fraction. Yeah, Connor?
So is this like review?
Yes? Well, you tell me, is it review?
Yeah.
You've seen this before.
Yeah, we did this all last year.
Okay? Okay, so in order to show the size of numbers in the relative order, we learn to graph them on a number line, right? And a number line, when you draw it, should be kind of like that. If you're going to put tick marks, they should be evenly spaced. Now, positive numbers, right, are to the right. Negative numbers are to the left. So if I label my axis here, right, 0, if I'm starting at 0, going to the left, the numbers go -1, -2, -3, -4, -5. I think I can leave it at that. If I go to the right, it's 1, 2, 3, 4, 5, 6, etc., etc. Okay, so now, if I was going to plot a number like -3 on the number line, I'm going to come over here at -3 and put a dot. Okay, if I'm going to plot -4, it goes here. So now, which number is greater, -3 or -4?
-3.
The numbers to the right are always bigger, which causes a lot of confusion later on in algebra 2 even, because it's got that opposite sense. I mean, we know 4 is bigger than 3, but -4 is not bigger than -3 because they reverse their position, right? So greater numbers are to the right. So -3 is greater. Okay, next. So you try it. Graph 4 and 0 and then tell which one is greater.
I have a little situation with you.
Draw a number line. Make the marks. Okay, so where should I have plotted? I needed to put some more numbers on my number line. So 0 and 4. And which one is greater?
4.
4. Okay, try 2 and -5. There's -5. There's 2. And 2 is greater because it's to the right. Okay, try -1 and 6. -1 and 6. Everybody agrees -1 is greater?
Yes. No, 6.
Of course, listen. I think 6 is greater.
It might be.
It's true. So here's the thing about integers and rational numbers, which Mr. Pace can tell you. because we deal with kids all the time. A lot of students, even in higher level math classes, you'll say, what's a rational number? And they draw a blank. I mean, they absolutely draw blanks. And sometimes even when you say integer, they're not sure what you mean by that. Here's the problem. When you take, let's say, the SAT test, not even the math portion, but it could be in the math portion too. They're going to use these words not like it's a quiz question, what's an integer, what's a rational number, but just like find an integer that, and you're supposed to know what they mean by that, right? So you need to know the meaning of the words. You could get that, if it's talking about some other topic, it's not math related, if they use those words, they still expect that you kind of know what it means. Okay, so here's the thing about integers. Integers are rational numbers because, as Adam said before, if you write anything over 1, then it's a fraction, right? So it can be written as a fraction, so it is a rational number. Even decimals, not all decimals are rational numbers, but if a decimal terminates like 0.5 and there's nothing else afterwards, or if a decimal doesn't terminate, like 0.33333, that's 1/3, we just put a 3 with a bar on the top of it, then also that is a rational number too. You can write it as a fraction. This one in particular is 1/3, right? We're pretty familiar with that conversion. But any pattern, 0.123 repeating can be turned into a fraction. Anything like that. So what are the only kind of decimals that are not rational numbers? It has to be non-repeating, non-terminating decimals. And there's one good example of them, pi. You've used pi before? 3.14, blah, 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 goes on forever, never repeats itself. The other kind of numbers that are usually irrational are square roots that you can't simplify. Like the square root of 4, you can simplify, but the square root of 5, you can't. That's irrational.
You said
No,
never.
because of the irrational number. So we're going to finish up a couple slides here. Tell whether these numbers are whole, integer, or rational. What about 0? So you're going to say it's whole, but if you say that it's whole, is it also rational? Then is it also an integer?
Yes.
Yeah, I should have put that. How about 0.5? Is it a whole?
No.
Is it
Rational?
integer?
Yeah, no.
So it is only rational number. How about -2 2/3?
That's irrational.
Only in the rational category. And how about -24?
Rational or integer?
It's an integer and it's rational.
Wait, the -2 2/3 can't be rational.
Yeah, it can.
I mean, it can't be. Oh, never mind.
It is a fraction, so it's going to be rational. Okay, so do this one. Do this one. Tell whether these are whole, integer, or rational. It's you try. Connor. Right? Do it. So what'd you say about the 3? It's whole,
Whole, rational, integer.
it's an integer, and it's rational. Remember, if it's in the whole number, it's automatically in the sets above it. What about -1.2? Not an integer. Rational only. How about -2? Integer and it's rational. And how about 0? All 3. Okay, so